Wow, somebody's here. All right, I don't know how this is going to go, but if you have any questions or if you just want to wait, that's fine. So we have some questions already. Will this stay up after the session's over? This is all new to me, but I checked and it looks like it can stay up. So I figured I'd leave it up through the end of finals, and then probably erase the embarrassing presentation for me. But then, even if you're not here at the session, you ought to be able to watch it later. Can we do an in-depth multi-level paging example? We did a lot of those before the previous exam. We can do it. Let me see what else is coming up as questions. So let's plan on doing a multi-level paging example. I'll try to go a little faster than we did before. The reason I'm leaning in like this is to be able to read the questions on the screen. Let me So let's go ahead and try to do the paging thing real fast. I'm going to mark on this and let me know if you can't see it. I don't know what the what the video quality is like on your end. All right, so I'm just going to make up an example of a multi-level paging problem, and we'll answer the kinds of questions that we've done on exercises or on quizzes and maybe on a previous exam. So usually I just start by making up a size of a logical address space. So let's say we got a computer system with a byte addressable memory. Let's say it's got a logical address space of, I don't know, 2 to the 22 bytes. That looks backward when I look at it, but I think as long as I just look in this direction, I should be okay. So that's how many different addresses a process can access. Let's pretend, and again, I'm just making this up. Let's pretend that a page size is 2 to the 8 bytes. So if we took that logical memory and we started breaking it up into page size pieces, how many pages would it have? And that's just division. So 2 to the 22 addresses broken into pages that are each 2 to the 8th in size gives us 2 to the 14th. Yeah, so it gives us 2 to the 14th pages for a process. So 2 to the 14th pages for a process. So if I had a page table, that's how many entries we need in the page table. Usually at this point, we try to make up a typical size for a page table entry. And on this architecture, it looks like sort of rounding up addresses would probably be 32 bits per address. So let's say you get a page table with 2 to the 14th entries, and each entry was 32 bits, so 4 bytes in size. So the total size of your page table is going to be 2 to the 14 times 4 bytes per entry. So let's call that times 2 squared, gives us 2 to the 16 bytes for our page table. I'm looking to see if anybody's complaining that they can't see this. Also, can you do a parity example? I second the idea of a parity example. So I think we're okay. Nobody's complaining about it, so I'm going to say you can probably all see what I'm doing. We're going to run out of board space soon, but we'll just erase and reuse. So that's how big a first level page table is. It's inconveniently big, and that's how big a page is, and that doesn't fit in a page. So multi-level paging would do the trick of breaking the page table into page-sized pieces and storing them in any available frames of memory. I brought down an improvised eraser for the whiteboard, and I'm looking for it now. And I don't see it. Let me run upstairs and get that. I apologize for the quick side trip. All right. So we got as far as saying that's how big a level 1 page table is in bytes, and that doesn't fit in a page. So we're going to break that guy into page-sized pieces. How many are there? How many pieces will there be? Maybe this improvised whiteboard was not a great idea. All right, so I just erased down there 2 to the 16th. That's how big our first level page table is. We're going to break it into page-sized pieces. Each of those are 2 to the 8th in size. So that gives us 2 to the 8th. So 2 to the 16th divided by 2 to the 8th. 2 to the 8th pages just to store our first level page table. So if we're going to store those all over memory, we need a second level page table that keeps up with where they are. And it has to have an entry for every page of the first level page table. So it's got to have that many entries. Probably the same as before. It's probably going to be 4 bytes per entry. So how big is the second level page table? That would be 2 to the 8th times 4 bytes per entry. So that's 2 squared. And that gives us 2 to the 10th bytes for our level 2 page table, which is almost small enough, but still too big to fit in a single page. So what what you'd typically expect to do is you'd break this guy up into page-sized pieces and scatter them all over memory. Let's see if we can fit that in the rest of the board. So that's how many bytes for the level 2 page table. I'm going to break it into page-sized pieces. How many pieces are there? So 2 to the 10th divided by size of a page, 2 to the 8th, gives us 2 squared pieces, page-sized pieces for the level 2 page table. We got to have a level 3 page table that keeps up with where each of those 4 pieces goes. And that's how many entries it's going to have. It's going to have 2 to the 2nd or 4 entries for that level 2 page table. I'll try and fit this in this space. So how much memory is that going to take? Well, that level 3 page table has that many entries. So that's 2 squared entries at 4 bytes per entry. So that's another 2 squared. And that gives us 2 to the 4th bytes for that level 3 page table. And that fits. So we only got 2 to the 4th, or we only need 2 to the 4th bytes, and a page is 2 to the 8th bytes. I apologize that the whiteboard didn't work great, but I'm going to assume that I talked loud enough that you could follow that. Just give me a new comment or add a comment if that didn't make any sense, or if it was impossible to see the board. I'm going to assume we've done that example, and I'm going to look for the next thing. We had a question about the unreliability of a distributed system. I'm trying to think about what we actually covered in that. I guess I remember we had a picture of sort of a made-up network, and we talked about how you might have hosts that are all connected by links, and you got to worry about the possibility of the links failing. You got to worry about the possibility of individual hosts failing. We didn't really talk about this, but you've got to worry about the possibility of, I guess, if links fail, then you've got to revise your routing decisions, and it might be that you send a packet out and it doesn't make it because the path it was intended to go on can't use one of the links it was depending on. I feel like we had a slide. I'll look for it real fast. The thing that I'm using to create this live stream, I don't think it lets me show my desktop. So I'll take a quick look at the slides and try to let you know a good place to look for that. I'm looking in slides for chapter 17 called Distributed Systems. Right, so we've got a picture of a graph. It's on slide number 14. It's just a graph that I made up. It's the one that later I put on top of the Candyland board. And this is really where I'm talking about the different sources of unreliability that, that there are, that links may fail or hosts may fail, that I've got to worry about. I guess this is one I didn't mention a moment ago. But I got to worry about competing applications, and congestion at individual routers in the network might mean that some messages don't make it through just because we can't afford to buffer messages forever. And if an outgoing link is saturated, then we might have to start dropping messages or packets. I don't know if that's what you're looking for with the question about unreliability of a distributed system. My guess is that's something on the study guide, and you're just wanting some clarification on what that's talking about. Feel free to post a fresh question if I didn't do a good job addressing that. All right, so somebody asked about a parity. So I'm moving on down the list of questions. Somebody asked about a parity example. We'll try and do this real fast. I don't know if you're asking about just plain old parity, or if you're asking about the Hamming code stuff that we did. I know in either section of the class, we had some examples on the slides that we didn't go over. I'll start with a really simple example, and then maybe what you really want to talk about is something like a Huffman code, and we can spend a little more time on that. I'm going to take this whiteboard down from the stand here so I can do a better job of erasing it, and then I'll put it back up. that works a little bit better. Okay, so let's talk about parity. We were talking about this while we were talking about RAID. So the idea is this is a very reusable mechanism for storing redundant information. The simplest thing we talked about is just the idea that if you had a bunch of bits, you could compute one redundant parity bit covering those. And so we might have made up an example, like let's say you've got 1 0 0 1 1 0 1. Let's sneak in another one. And let's pretend you wanted to store an even parity bit for those. I apologize, I'm going to change my example because a more typical example, like if you're thinking about storing a parity bit for an ASCII character, you might have 7 bits that select the character, and then within a byte you might have an extra bit that you could use as parity if you wanted. So there, if we were doing even parity, the way I try to remember that is I want an even number of ones in the number when I'm done. So there's 1, 2, 3, 4. There's already 4 ones. So if I was going to put the parity bit right there, I would put a 0 there. And then I've maintained even parity. When we looked at this example, or this kind of example, we said, well, this would be great for detecting single bit errors. If you transmitted this and then maybe 1 bit got written out, but then when you read it back in, you didn't get the thing that you wrote out. As long as it was at worst 1 bit, you could tell that something went wrong. And then from that, we said, well, that's worth something, but it doesn't tell you how to fix it. It doesn't tell you which bit was wrong. And from that, we started talking about Hamming codes as sort of a simplest way of building a code that can not only detect that something went wrong, but correct maybe single bit errors. I don't know if that's what you wanted for parity. I'm looking at the comments. Someone else says, can we do a parity example? I second the idea of parity. So it sounds like you want something, probably something more on that. Oh, the study guide hasn't been updated. I need to do that. I said I would do it and I didn't get that done. I'll try and do that right after I appreciate the reminder on that. I'll try and get that done right after our meeting tonight. So on this parity example, do you want to do a Hamming code example? Is the parity bit always the first bit, or alternatively, will we be told which bits in the bit string will specify parity? I guess the reason I did it like this, I think my example in the slide has it sitting over here. And I guess it depends on whether you're thinking of transmitting those bits or not. I guess when I put the empty box over here on the slide, I was thinking, well, that's something extra we're going to add on after the data bits. But if you're looking at it as a byte, I think it makes, if you're looking at it as an ASCII character that only needs 7 bits for the code, in an ASCII character, the high order bit is unused. So that's why for this example, I put it over here. I don't think there's a universal answer for here's where it goes. I think if I asked you to do something like that on a test, kind of like we did on one of our quizzes, I put in a bunch of boxes with bits in them, and then I left you an empty parity box to fill in. And then I guess from there, I think it'd be clear where the bit goes in that case. When we're doing our Hamming code examples, I know I had 4 data bits, and then I put 3 parity bits, I think, to the right of those. And if I asked you something like that on the exam, I would probably do the same kind of thing, but I think it would be clear. I think it would be clear where you're supposed to fill those in. Okay, so I'm going to say I answered the where's the parity bit go? I don't know if, so there's a question that says, what kind of protection security questions are going to be asked on the exam? I don't know if I can answer that. I would say the study guide is a great place to look for that kind of thing. I tried to list the stuff that I might ask you about. Thinking about it, and just thinking back to it, we snuck in some definition of terms on that, things like domain and objects. We talked about the idea of an access matrix as a sort of made up way of trying to write down the protection you want enforced. We talked about different notations, different things we might want to put in the access matrix, like typical access rights, like the ability to read or the ability to write or execute an object. And then I think the more interesting stuff, I mean, I feel like I could probably ask some questions about that, but I think it got more interesting when we started talking about actual representations. So we said, well, you wouldn't really store this in a big table. You'd store it in an access list or a capability list or some kind of lock and key mechanism. And there we started talking about some trade-offs for that. So I think to get some maybe more detail on what kinds of protection security questions you might get, I would take another look at that section of the study guide. Can you do a level 5 parity example similar to the quiz? Yeah, in fact, I think for the two sections you had we could do one from the quiz, but I think you probably had different questions on that quiz. I'll just make up an example and we'll give it a try and see if it's what you're looking for. By the way, we're filming from my basement, so that's why it looks like that. That's why I'm wearing this, because it's cold out here. All right, so I'm going to draw, I'll try to fit in, kind of like we did in class, I'll try to fit in pictures of 5 hard disks or pretend hard disks. My artwork is not great on this, and the last guys would be pretty small. All right, so pretend those are 5 hard disks. The idea of level 5, so if I had to draw this picture and say, well, pretend this is level 5, the difference between that and level 4 is just who's doing the job of parity. In level 4, the same disk is always responsible for parity, but in level 5, they take turns, and we talked about some reasons for that. So to make this picture make sense, I have to pretend it's in blocks. So let's pretend there's a block on each of these disks has a first block on it. And kind of like in our picture, we could say, well, maybe this guy's doing the job of parity for that first block. And then maybe for the second block, maybe it's this, like we did in class, maybe it's this guy's turn. And then for the last block, maybe it's this guy's turn. Of course, my pictures are ridiculously small examples. Real disks would have, we could do the math on this, but I want to say millions of blocks of data, and that each probably be 4 kilobytes in size, or between 512 and 4 kilobytes. So we're pretending these blocks are tiny, just so we can fit them on an example. Let's pretend this is the disk that failed. And I'm just going to make up some bits. So we'll pretend this guy failed, and we went out and bought a replacement and plugged it in. And I'm just going to make up some bits for the other disks. So then the first block on that guy was 0101. Pretend this guy was 1111. Pretend this guy was 0110. Pretend this guy was 1101. So this, for that block, this guy is the parity block, but it doesn't really change what we have to do when we fill this in. We're still kind of doing the same thing. We want to fill in the bits, or we want to restore the bits on this disk so that we maintain even parity. And when I say that, I mean, well, this bit, the first parity bit on this disk was computed, we're pretending as even parity, covering that bit, and that bit. So the first bit on all the other disks. So when we restore that, we've got 2 choices for what it could be. We're going to fill it in with the one that maintains even parity. So looking at the first bits, there's a 0, 1, 0, 1. That's already an even number of ones. So that first bit there must have been a 0. Otherwise, parity would have been wrong. We'll continue with this example. So the next bit, 1, 1, 1, 1. They're also already an even number 1. So that guy must have been a 0, or parity would be wrong. Continuing, 0, 1, 1, 0. You might get unlucky here. So that guy must also have been a 0. Let me double check. 0, 1, 1, 0. Yeah, that guy must have been a 0. And 1, 1, 0, 1. That guy must have been a 1. Otherwise, even parity wouldn't be maintained. Do you want to do another row of that? Let me catch up on questions. All right. All right, so there have been a lot of questions since last time I looked at this. All right, so I'm going to say we did part of a level 5 raid. On the next row, we might be pretending that's the parity block, but it wouldn't really change how we fill this in. We're still doing the same thing. We're trying to fill in each bit so that even parity is correct when we're done. All right, so somebody said, will this stay up? And it looks like I'm planning to leave it up at least till the end of the exam period. All right, continuing. Can the exam, I thought the exam key for exam 2 was up. I'll check on that. I usually put it up when I return the exams. Maybe I made a mistake. What if I can check? I was going to say what section you're in, and that'd make it easier to check. And if we have a slow time during our review session, I can take a quick look at that. Oh, it's named incorrectly in Moodle. I'll have a look at that, and I can fix it if that's what's wrong. All right, good. So I'm glad I didn't miss that. I apologize if I gave it the wrong name. So I'm reading the one about asking for clarification on deadlock detection versus deadlock avoidance. Specifically, the graph detection method on the slides, as in the steps taken. All right, so the first part of the question, asking about deadlock detection and deadlock avoidance. They're two different techniques for dealing with deadlock. As far as the algorithm, they're related. Deadlock detection says you're going to give processes all the things they need to potentially make a deadlock. And when I say that, I mean the necessary conditions, so they can ask for resources. You're not going to take the resources back after you give them to them. They can have some resources and they can ask for more, that kind of thing. Deadlock detection says you're going to let deadlock happen, and then you're going to have at least a way of noticing when it happened. And we'll make up an example and do one of those here. I think that's the easier of the two. Deadlock avoidance makes us, we have to extend our graph notation a little bit for that. We have to do a halfway decent job of that. We have to have a notation for things a process might ask for in the future. And that's where the idea of claim edges came from. Let's do a deadlock detection example that I'll just make up. And then if we want to do an avoidance example, it'll be a little trickier, but not too bad. I'm going to do the same thing I did a moment ago to erase this. All right, so I think we're going to do a deadlock detection problem. So I'm just going to make up a graph. Let's pretend you've got a resource, and resources are little boxes. The idea is these represent real resources you might allocate on a computer, so something like blocks of memory or physical devices like a tape drive or something. For these examples, we usually don't make up realistic examples. We just call them something like R1 to say, well, just pretend that's a resource. Let's pretend we got another resource, R2. The little dots inside them, those are instances of the resource, and these problems get more interesting if you assume resources can have multiple instances. And when you want an instance, you're happy with any of the instances. And some resources really are like that, like blocks of memory is usually the first example I think of. If you need another page of memory, you might have millions of pages available, but any one of them is good enough for what you need, at least if you've got page memory and you can graft any one of them into your address space. All right, so we'll make up some processes. Call this guy P2. Call this guy P1. Let's call this guy P3. And then let's just start. I'm just making up this question. So let's say, well, pretend P1 has an instance of R2, but it wants an instance of R1. Pretend both of those are in use by these two guys. But meanwhile, P3 wants an instance of R2. Is this graph deadlocked? It's not, because, well, P2, well, sorry, this isn't quite what I planned to do. We'll add some arrows to it to make it more interesting in a moment. P2 has everything it wants. So as long as it doesn't ask for it, so this is what the deadlock detection algorithm does. And that was kind of the original question. So before we start doing it, let me just kind of remind you how it works. It says, if you want to know if this graph is deadlocked, take a picture of the graph and then repeatedly look for a process that has or can have every resource it wants. And then pretend it doesn't ask for anything else. So eventually you get the instances of its resources back when it finishes, and then repeat. You're always trying to find a new process that can have everything it wants, and then you pretend it finishes and take back all of its resources. If you can finish up all the processes like that, you can make them go away, then the graph wasn't deadlocked. If you can't, if you get stuck and there's some processes that can't have everything they want, but you've already, you can't find anyone else who can have every resource they want, then the graph is deadlocked. So you've already run into a deadlock. I don't think I'll erase. So normally if I was doing this in class, I would, and we said, well, is this deadlocked? I'd start erasing stuff to run the algorithm, but let's see if we can just talk through it. So in this picture, P2 already has everything it wants. So we could start by erasing that arrow there, and then repeatedly finding a process that can have everything it wants. So once we get back this instance of R1, now this guy, P1, can have everything it wants, so we can erase both of those arrows. And we could have started here. P3 can have everything it wants, so we can take these arrows back. Let's add some arrows to try to make a deadlock, just to have a different example. So what if P3 already had an instance of R2? There's nothing wrong with that. I sometimes get a question about this. Is it okay to have an instance of a resource and then ask for another instance? And yeah, we're assuming that's okay. That makes sense if this resource was something like memory, where maybe you've got a region of memory, but you need more memory to make progress. So even with that, we're still not deadlocked because, well, P3 can't make progress right now. It can't have the instance of R2 that it's waiting for. This guy can't make progress, but P2 can. And as long as P2 doesn't need anything else, and looking at the state of the graph right now, P2 has everything it wants. So we would erase that arrow, and then kind of like we did before, P1 can have everything it wants, so we'd erase both of those arrows. And then finally, this guy can have everything it wants. So this is still not deadlocked, but if I wanted to make it deadlocked, I could sneak in one more arrow like that. And now, well, P3 is stuck because it wants an instance of R2 and it can't have it. P1 is stuck because it wants an instance of this and can't have it. P2 is stuck because it wants an instance of R2 and can't have it. So here, if you tried to run the deadlock detection algorithm, that condition on the outermost loop says, while there's a process that has everything it wants, keep pretending they finish and you get all their resources back. Here, we kind of get stuck before we even get started. There are no processes that can make progress. But that's not, you could have a deadlock even if some processes could make progress. I'll make up a silly example because I can always just add stuff to the graph and I could say, well, what if There's R3 up here, a resource 3. And what if there's a process 4 that wants that? Well, it can have it. So if we take this new graph that I just added some extra stuff on the side and said, is it deadlocked? Well, now the deadlock detection algorithm would say, P4 can have everything it wants. So eventually I'll get those resources back. But now you're stuck. These 3 remaining processes are part of a deadlock. P4 wasn't part of the deadlock. If you're going to fix a deadlock like this, we already said you're going to have to kill a process. And this sort of shows us, well, killing P4 doesn't help. So we spent a little bit of time. I made up a graph. I changed it and added stuff until we ran into a deadlock. And then I tried to remind you of the deadlock detection algorithm. I'm looking back at the original comment that said I want asking for some clarity on deadlock detection methods. So hopefully that did what you wanted. You can ask for another example or ask a related question if I didn't get to what you were looking for. Can the answer keys for the quizzes be uploaded? I don't usually do that. If you have questions on a particular quiz, we can take a look at that, but I don't usually post those. I count on the grading helping with that. And if something doesn't make sense, we can talk. It's the kind of thing that I try to talk about in class. Will we get a little Hamming code? Maybe. So I'm looking at the question. It's third from the bottom for me that says, will you get the little Hamming code cheat sheet on the final? If I ask you a question like that, I will probably give you a cheat sheet because that's going to make it easier to grade. And the Hamming code that I made up was arbitrary. I just made it up. It's no better than anyone else's Hamming code. So I feel like if I asked you a question like the one on the quiz, I would want to give you that cheat sheet. But I could also ask you some other questions, like I could, that kind of show if you understand how Hamming code works, that where you wouldn't need a cheat sheet to answer that. So for instance, I could ask you to make up your own Hamming code that's, I want to say that's different from the one we did in class. And if you understand how that Hamming code example works or why it works, there might be a little trial and error, but I think you could come up with a code on your own. So I feel like I could ask other questions besides just fill in the parity bits for this. But yeah, if I asked you a question like that from the quiz, I would probably give you the same little cheat sheet. Are vocabulary terms from all semester fair game? Yes. I guess the only thing I should say is, well, we never got to 2 of our chapters, so I'll sneak in and at least put a note on those lists. I think the ones we missed were chapters 11 and 12. So I won't ask you vocabulary questions from the stuff we never got to cover. But older terms, I think, are still fair game. I'll try to put a little more emphasis on the stuff we've covered more recently. I made the term lists by going through the book and looking at all the terms and trying to pick the ones that I thought were most important. So I left out quite a few of them. But I would say you probably want to feel like you know those terms. Deadlock detection. Oh, good. I'm looking at the last comment that says, yes, this is what you were looking for. And when I make up these questions for the exam, this is kind of what I do. I just make up a graph and start adding edges to it. And then usually I try to make sure I've got some that are deadlocked and some that are not. But I guess I could make them all deadlocked or not deadlocked. I don't know if that's a good heuristic for looking for an answer, but I do probably try to come up with a little variety in the examples if I ask you one of those. What did I say I would do? I said I would check on, so I'm going to go check on the thing that I said. I'll see what's wrong with the naming of the study or of the answer key from exam 2. And I'm assuming other people might be asking questions, so by the time I get back, there may be a few questions to take a look at. All right, I'm looking at section 1. All right, so section 1, it says exam 2 key and grading guide. So I'm going to say that's not the problem. I think, I mean, I think it is named wrong, but it's not that far off. I think it's probably the thing that says sample solution and grading guide, and maybe I should, certainly I could make that consistent between the two sections. So I'll fix that. Let me go see if we've got more questions. Yes, yeah. So I'll fix that. But yeah, that is the one that I mean. I guess I was thinking it's a sample solution for the exam. But yeah, I mean, also that could sound like it's the sample exam. But I'll go call it something like exam 2 key and grading guide, like probably it's done earlier in the on the web page. Can you go over the protection security quiz? Yes. What section are you in? No, so I'm looking at the last question. I'm waiting to hear what which sections protection security quiz we need to talk about. Monday, Wednesday section. That would be section 1. So we'll take a look at that quiz, and I don't know if I have a good way of showing it to you, so I'll just describe what's on it for the people in the other section. So there was one other thing I wanted to respond to. Oh, the part about a practice final. I don't usually post a practice final. I'm thinking, or I've always thought, well, you've got the examples from the previous exams. The structure of the final will be the same. It'll be a little bit longer. I usually shoot for making it about 50% longer, maybe not quite that much longer. All right, let me go try to find the protection and security quiz for section 1. All right, I'm looking at quiz 18 for section 1, which looks like it's some stuff on protection and security. We'll do this one, and then we'll do the one that comes after it. So the first question is, in the access matrix, what does it mean if an access right has a star next to it? That just means that you are given permission to copy it. Even that, I know when we covered that in class, we said, well, there's still more you could say. When you copy an access right, can you give away the ability to copy that access right? So just having that extra bit of notation, I don't think that tells us by itself. I don't know if that'd be super useful in practice, but that is what the star means. Moving on down, so the second question was, which representation of the access matrix, sorry, I apologize, what representation of access makes it easy to store default access rights for an object? So every domain can have some base level of permissions for an object. I think the best answer for that is access list. That's where every object has a list of who can do what with it. And there you could just add a default access right to that list. And the last question is, Unix systems have a simple mechanism for letting a process change its protection domain. What is it? And there are a bunch of answers, but the right one is it's the set UID bit. if it's set on a file, then whenever you run that program, you have the effective user ID of the user who owns that file. So you get to act as them while you're running it. Probably, if you're interested in the protection and security quiz, maybe you're interested in the next one. Let's see what's on that. And I think this may have a lot in common with the other section, because I'm not sure we didn't get to do the middle question on this for section 1 because we didn't cover it. So the first question is, in a blank attack, the attacker is able to read, create, delete, and modify messages being exchanged. So that is a man-in-the-middle attack. The idea that you can intercept communication going in both directions, and you can kind of replace it with your own message. The next one I think is the interesting question. It says it's using the notation that out of your book for talking about encryption. It says assume M is a message, and case of B and D are the public and private keys for a user. Which of the following best describes a digital signature for M? So I think this is really just seeing if you can use that notation or if you remember it. Thinking about digital signatures, the first thing you do is you compute a hash or a cryptographic hash of the message. So looking at those 4 answers, the first thing I'm looking for is, well, which one hashes the message? And it's, I guess I could try to write this down in the chat. That might be, well, I guess I'll try and write it on the whiteboard. So I got a bunch of other answers that are just things I made up with different parts of the notation. But if you're doing a digital signature, like I said, the first thing you would expect is a hash of the message. So in that notation, it would look like that. So compute a hash of the message. And then the next thing you would do is encrypt the message with your private key. Then anyone can decrypt and can, sorry, I said encrypt the message, but I shouldn't have said that. You encrypt the hash of the message with your private key. And then anyone could decrypt to recover the hash, but only you could have prepared it in that way. So we just have to take this and then run it through whatever the notation is for encrypting with your private key. And encryption, we pretended, was a function E. If you give it a key, and it says at the top of the question, K sub D is the private key. So if E applied to K sub D is the encryption function for encrypting with your private key, and then if you take that and apply that to the cryptographic hash of the message, then that would be a digital signature. There's a bunch of other answers there, but they're mostly nonsense. So hopefully, I guess I would say this is asking 2 things. It's asking, do you understand this notation for talking about encryption and hashing? And then it's asking, well, do you remember what a digital signature is enough so that you can apply that notation to it? We're almost done. All right, the next question is asking about the difference between a stream cipher and a block cipher. A block cipher is really just, it's noticing this idea that some encryption algorithms work on fixed size blocks of data. So if you give them a message that's not a multiple of that fixed size block, then it's either going to have to be padded to that block size. And I guess also they, I apologize, I'm trying to think. Yeah, I was about to talk about cipher block chaining, but I don't think that's in the question. Looking at the answer, so again, it says, what's the difference between a stream cipher and a block cipher? I'm looking at the answers. I'm skipping over the wrong ones. Oh, so the third answer says it's whether or not they work on individual bytes or blocks of data, and I would say that's the best answer. Sorry, that was probably a long-winded answer for a short question. All right, so I'm trying to catch up with where I was before I started answering that question. Oh, so I'm looking at the question that says, when will you update our exercise grade? I'd hope to get to that today, or really compute the overall exercise grade. Moodle's probably computing an average, but it just averages them all together. I've got a little script that'll compute it for me, and then I'll upload it into a separate column in Moodle. I'd hope to get that today, but I don't know if I'll get it done before I run out of time today. But I'll try and do that tomorrow. I think I can have that done before you have to take your exam. Uh, Related, grading is continuing on homework 3, and I just put together the grading materials for homework 4. So hopefully that will get done soon. I know that you have to look at at your grades for that and look and see if there's maybe any mistakes in how something is graded. So we want to make sure that we give you some time to do that. All right, so someone wants me to do a CPU scheduler. I can give that a try. Shortest job first or shortest remaining time first. I guess if I had to pick what I would do, I'd do shortest job first because it's easier, but maybe we'll do shortest remaining time first just to have a better example. I'm going to take this away and I'll erase it. I'll be right back in a moment. All right, so like I said earlier, I've got this hoodie on because it's cold down in my basement. But nothing will warm you up like erasing a whiteboard that doesn't want to erase. All right, so we said we would try a CPU scheduling algorithm. So let's try shortest remaining time first. We have to make up some processes. So pretend we've got process 1, process 2, process 3. I'm just trying to decide how difficult I want this to be. Let's put in a 4th process. And then for each of these guys, we'll make up an arrival time. We've always started with time 0 as the arrival time. And that makes sense because otherwise the CPU would sit idle at the start. So if I was just making up this problem, I would say maybe that guy arrives at time 0. Maybe this guy arrives at time 2. Maybe this guy arrives at time 5. And maybe this guy arrives at time 7. Let's say this first process has a burst time of 3. So then the other thing we need to know, of course, is, well, how much CPU time do they need? This is, of course, we've talked about this a bunch. This is the reason you can't really do shortest job first or shortest remaining time first perfectly, because the OS doesn't know what the next burst length is going to be. But to simulate this or to see how these schedulers work, we're just pretending that we know that. So this first guy, let's pretend has a burst length of 3. Let's pretend this next guy has a burst length of 8. Pretend this next guy has a burst length of 2, and then let's pretend this next guy has a burst length of 1. I'm just making these up, so I don't know how bad this schedule might end up being. We'll try and draw it down here at the bottom. At time 0, the only guy we can start running is P1. So we'll pretend P1 runs up till, well, the next thing that's interesting that happens is at time 2, P3 arrives. But P3's got a burst length of 8, and P1, well, it had a burst length of 3, but it's already run for 2 milliseconds, so now it's down to just 1. So in this case, we'll stay with the guy we were running. So we don't switch, we don't preempt P1 to give P2 a chance, because it needs a lot more CPU time. And that means P1 will get to run all the way up to time 3 when it finishes its burst. Then we look back at the queue. P3 hasn't arrived yet. It doesn't arrive until time 5. P2 arrived, so it's arrived. It's got a big burst length, but we've got nothing else to do. So we'll start running P2. P2. It gets to run for what started at time 3. So it gets to run for 2 more milliseconds before this guy arrives. At that point, at time 5, we'll pretend we're up to time 5 here. This guy has 6 milliseconds left because he ran for 2 milliseconds there. And this guy only has 2 milliseconds. So at that point, P2 is going to be preempted at time 5. It's going to go back on the queue, and we're just kind of keeping up with this in our heads, but that 8 is now a 6. It's already had 2 milliseconds of CPU time. This guy gets to run, oh, this could be an interesting schedule. This is to be a little bit busy. So, sorry, P3 gets to start running at time 5. It only needs 2 milliseconds, so it will get us all the way up to time 7 when 2 things happen at once. And I kind of misspoke a moment ago. I said this would be an interesting schedule because I thought this guy would get a chance to run again for a moment, but it doesn't because P3 finishes up its burst and P4 arrives both at time 7. And at that point, P4 is looking like a good guy to run because he only has 1 millisecond remaining. So we will let him have 1 millisecond. That gets us up to time 8. That's P4. 8. And then everyone's done except P2. We said it still needs 6 milliseconds of CPU time. So, and no one's left to get in its way. That'll get us all the way. So if you were counting, for example, if you were counting waiting time for this schedule, let's pick P2 because it's the most interesting to think about. It arrived at time 2, but it didn't get to start running until time 3. So it had 1 millisecond of waiting time right in there. And then it got to run for a moment, but then other jobs with shorter bursts got in its way. So it had another, looks like 3 more milliseconds of waiting time there. So it looks like its total waiting time is 1 there plus 3 more here. So 4 milliseconds of waiting time for that guy. Just picking other examples, this guy P3 didn't wait at all because it got to run as soon as it entered the queue. The same for this guy. Yeah, same for this, same for P1. So I think everyone else has a 0 waiting time. The P2 kind of waited a little bit there and then more in the middle here. So I'm going to say we did an SRTF example. SJF, I don't think we'll work it, but if you wanted to compare it, the difference would be right here. SJF is shortest job first is non-preemptive. So that means once you pick a job, you stay with it until it finishes its burst. So for this schedule, that preemption wouldn't happen. P2 would have gotten finish all of its 8 milliseconds of CPU time. All right, looking on down the list of questions, could you give any pointers as to how, for the sockets section? I'm not, so I would not ask you to write that socket code. That, and maybe I'm misunderstanding your question. I've written that socket code, but I always say I think I've only ever written it once. And every piece of code that I've ever used afterward has been maybe a modified copy of that code that establishes a TCP connection. I want to look at the study guide for this because I'm not 100% sure what's there. I would say the Java API for working with especially TCP sockets is simple enough that you could probably code that from memory, but I definitely wouldn't expect you to write the code for establishing a TCP socket in C using the sockets API directly. But you should kind of know what those calls mean. So for instance, if I said, well, what's the sequence of calls the server might make to start accepting connections? You probably could list those, and even if, even that I would see as maybe a little bit of a hard question. I feel like if I gave you a question like that, there'd have to be a little bit of slack in grading it. Maybe it'd be okay if you got one of them wrong or something like that. But I think the more important thing, rather than being able to write that socket code, would be kind of knowing what each of those calls, in general terms, what each of those calls does. So I'm reading the one that says, I assume that you can all see what's in the chat window. So I'm down to maybe the third to last one. To what extent should we memorize code for writing? I would say, so I feel like that is, so I'm looking at a question that says, I think, how much do we need to know how to write code that does threads? And I would say you ought to be able to create threads in the POSIX or the pthreads API, the POSIX API, or Java. You ought to be able to do things like wait for the threads to terminate using join. You ought to be able to pass arguments to the threads. We do look at some API calls where I don't expect you to be able to reproduce that code, but I would say things like starting a new thread, using that threads API, things like starting new processes in Unix, calling fork, calling wait. I would expect you to be able to write a little fragment of code that does that kind of thing. And so I feel like that is kind of spelled out on the study guide. So I'm looking at the second to last one. So there is a question about the keys for the exam, and I think those are already uploaded. Someone asked about that a little bit earlier. I'll go ahead and double check that. I can go ahead and take a look at that right now since I'm caught up on the questions. All right, so exam 1 key looks like it's there for section 2. I'm just checking to make sure I'm looking at the right section. Oh, I'm sorry if I misunderstood. The keys for the other sections exams. I don't plan on doing that. It's not that those exams are secret or anything like that, but I feel like if I was teaching this class in any other semester, you'd kind of have the materials that pertain to your section of the class, and you wouldn't. I don't know. Maybe I'm comparing it to the wrong thing, but I hadn't planned on distributing that between the different sections. So normally when we have a on-campus review session, if I don't get questions, I just start making up stuff to talk about. It doesn't seem to work as well when I don't have an audience in front of me. So I don't know if I could do that. We talked earlier about how I have not done what I said I would do, and that is sneak in and update the study guides for the 2 sections. I meant to do that right after class on Thursday, and I didn't get it done, and then I forgot about it. So I will get that done tonight after this session. So you can look for that being updated soon. Mostly it'll involve deleting or at least commenting out the material for the 2 chapters we didn't get to. And I think there was one topic or so at the end of chapter 10 that we didn't quite cover, so I'll mark that out. And we go over some disk scheduling algorithms like clock and shortest seek time first. Oh, yeah, sorry, I read that wrong. I pronounced that, or I think of that as C look. We can, I don't want to have to do the math on this, but we can give it a try. Yeah, let's talk about that. There are some examples in the slides. Sorry. And I know, I'm trying to remember if we did some of those. I think both sections may have gotten to do a quiz that had some of that. I'm going to go erase this, and then we'll do some hopefully smallish disk scheduling questions. All right, I'm just going to make up an example. We'll do shortest seek time first. The risk of making up an example for this is I might accidentally put in a tie. If I prepare a question for the exam, I don't have to worry about that as much because I can check in advance and try to make sure there's either no tie or I think ahead to how I want you to resolve a tie. That's usually what I try to do, but I know on our previous exam, we have a CPU scheduling question where I made a mistake on it. And there was, I think we still tried to grade it in a way that made sense, but there was a tie in at least one place that I didn't really need to have there. All right, let's pretend you've got a disk. Let's pretend your innermost cylinder is cylinder 0. And to make the math small, let's pretend the outermost is 19. So when we're seeking for particular cylinders, we're going to be in this range inclusive. Let's pretend you're on cylinder 5. So the head right now is over cylinder 5. I'm just making that up. And then I'm just going to make up some requests. So pretend you got a request. Let's pretend your queue has a request for cylinder 7, a request for cylinder 19, a request for cylinder 3, a request for cylinder 16, and a request for cylinder 2. All right, I'm making this up, but what would happen in shortest seek time first? Well, if you're starting out at cylinder 5, you could go to the right to get request 7, or if you went to the left to get request 3. Oh, and I made a tie, which I didn't want to do. Let me cheat and change this. So let's change this. Let's change this 3 to a 2, and then let's change what used to be a 2 to a 1. And that'll at least break that tie starting out. So if you're starting at cylinder 5, 7 is a little closer to you than 2. We're going to go to the right up to cylinder 7. And you just, up to cylinder 7, and you just seek for 2 cylinders worth of seeking there. And then when you're at 7, you've got a choice between going up to 16 for a distance of 9 versus going down to 2 for a distance of just 5. So you're going to go down to cylinder 2. I'll mark that up there. So you're going to go get cylinder 2. That's a distance of 5. And then you're going to go on and get cylinder 1, because that's only 1 hop away. I didn't give myself enough space here, but we're almost done with this. And then looking at these, you got 16 and 19 left. So you go up and get 16. Add a seek. You say the seek 15 cylinders there. And then you're going to go on up. for another 3 cylinders worth of seeking. For adding all of this up, you can add all the individual numbers. The 6 there, plus 2 is 8, plus 15 is 33, and then plus another 3 for 36, unless I made a mistake on that. Like I mentioned, these ones that do the wider sweeping, it doesn't matter as much here, but for a bigger problem, these sometimes are easier, because instead of having to add up every little hop, you could say, well, you started out at cylinder 7, and then you went down to cylinder 1 for a total of 6 seeking in that direction. And then when you went from 1 all the way up to 19, that was 18 there, rather than having to add all that up. I'm sorry, my picture's kind of ugly. Let's do, someone said, could we do shortest seek time first and C look? So let's give that a try. I'll try to, I'm just trying to decide. I guess I'll try and draw it up here. Probably erase this. This is not a premium whiteboard. If you go out to Lowe's, you can buy whiteboard material for cheap. And unfortunately, that's what you get. All right. So if we were doing C look, all of our examples in class, I think, we pretended the head was moving in the direction of higher cylinder numbers. I'm trying to decide if we should do that. I guess we'll keep doing that, because if we're doing C look, it's circular, so we only serve requests going in one direction. So same thing, if you started here at cylinder, put a 1 there for that. You started at cylinder 5, and let's pretend you were serving requests going in the higher cylinder direction. Well, you would go up to cylinder 7. And since I wrote them down up here and they're already in sorted order, it's kind of easy to ignore the order down here where they arrived and just service them based on the order they are, the order I drew them up here at the top. So if you're in 5, you seek up and service the request at 7, and then the request at 16, then the request at 19, and then for C look, you turn around and you run all the way back to the start of the disk. Actually, for the look version of this, I said you run all the way back to the start of the disk, but really look goes to the first request. So in this case, you would run back to request for cylinder 1, not all the way back to cylinder 0. So you'd start there, you'd service that request, and then you'd move up to cylinder 2 to service that last request. So if what else could I write down for this? If I had to write down the order in which the requests are satisfied, the head starts out here, and we're servicing requests in the direction of increasing cylinder numbers. We're going to service these requests in the order of 7, 16, 19, and then back to 1, and then up to 2. I don't know if that's what we were looking for. It's just a little example that I tried to make up. Yeah, C look. Sorry, I just read it wrong. All right, study guide says for CUDA programming that we don't need to make perfect code, but how general do we need to be? Like pseudocode, or just an idea of what each command does? I guess I'd be looking for certain parts of your program. If I had to pick kind of what you have to remember to use CUDA, I would expect you to remember, well, I've got to allocate space on the device, and then I might need to copy data over to the device. Out of my memory, I don't know if I could get the CUDA malloc and CUDA memcopy calls just right for that. But even if you got some of them wrong, I would still expect to be able to tell what you were trying to do. So certainly, if you got parameters out of order or something like that, I don't think that'd be a big deal. But having a call that was clear that you were allocating space on the device, and then moving stuff back and forth between the host and the device, and then having a call where you start up a kernel. That's another place where the syntax is goofy. I probably wouldn't expect you to get it exactly right from memory, but there's certain things I could be looking for. Remember that call had, so when you execute a kernel on the device, you've got a name for a function, and then the function has parameters that get passed to all the threads that get made. And then the goofy part was in between here, there was a triple angle bracket. And then there were parameters that gave the number of blocks in a grid and the number of threads in a block. And even if you got pieces of this wrong, I guess I'd like to see something that shows that you remember when you farmed off computation to a graphics device, you told it the dimensions of the threads you want to create. I think I could ask you a question where you had to write code like that. And I might do that. I feel like kind of like your question is asking, how tolerant would you be? And I know this is vague, but I think we'd have to be forgiving, if this notation wasn't exactly right. But I could also ask a question the other way, where I could show you a piece of code and ask you to explain what it's doing. I feel like I could ask either question. I think the second version is probably a more interesting question to show that you understand this stuff. But I guess I wouldn't rule out asking you to write some code that shows that that you picked up something from doing that CUDA programming problem. So while I was waiting on the question, I snuck in, and I think I made the names for the keys more consistent. Yeah, so on section 2, I think both of the keys for the previous exam now say key and grading guide. I know that was not necessarily what the question was about, but I did fix that. I should be erasing this whiteboard, because if there's another question, you're going to want it. There are no more questions. We'll give it some time. What else could we talk about? Talk about snow. We got about a foot of snow here in Chapel Hill. I don't know what Raleigh was like, but it must be bad if they're canceling a day's worth of exams. But there's a way I can tell how many people are on this. Looks like 25 of us. So I'm going to say people are still hanging around. What can I tell you in general, the exam? It used to be that I would sometimes go back and try and deliberately cover areas that weren't on a previous exam. But I don't think that's going to happen much this semester, because by teaching the 2 sections of the class, I have a harder time keeping up with what has shown up on one section's test or another. So I would say I will try to just have a random sample of material from the study guide. And it's possible there will be a similar question to what showed up on the previous exam. If so, it's just coincidental. I'm not trying to do that. I'm not trying to avoid it. It's just with 2 copies of the same class, it's harder for me to keep up with that. A foot of snow? I claim it's a foot of snow. I mean, it compressed a little bit yesterday. I could, no, it's too dark outside. But yeah, we got a good bit of snow. Got up to 15 inches in the mountains. Oh, so I'm looking at that last question that said, yeah, in both sections we talked about, I think it was level 6 of RAID, having a way of doing multiple redundant blocks. And I know I always try to remind people or make the point, well, there's no value in having 2 copies of the same redundant information. If you lost both, like having 2 copies of plain old parity data, because if you lost it, you go recompute it. If you lost 2 other disks, having 2 copies of the same information isn't going to give you any more power to recover that. I don't know how, so if the question is, how do you compute other blocks worth of redundancy? I don't know for a fact how that's done. I've always assumed it was done using linear algebra. I've seen other mechanisms that work kind of like that, and they give you the ability to recover something as long as you have enough linearly independent blocks of data, but haven't done enough looking at how RAID level 6 actually works to know if that's what they use. I won't ask you. I think the important thing for us is by having multiple blocks worth of redundancy, we can tolerate the loss of multiple disks simultaneously, and that lets us, even with RAIDs that might have a lot of disks, that lets us make a probabilistic argument that we can control how likely it is we're going to lose data. So yeah, the important thing, I guess, is RAID level 6 is not just going to keep 2 copies of the same parity information. What chapter from the most recent material is the most important to know? I think some of the most useful material is probably the networking material, but I don't know if I've got as much testable stuff from that as some of the other sections. Probably the protection and security material. Normally we would have gotten into file systems a little bit more, and we didn't make it that far, so that's a bunch of stuff I don't get to ask you questions about. Probably I mean, this is not your question, but if we had gotten into that, probably there's more testable material in that file system stuff than in the remaining chapters. I guess I'm thinking back, as far as what we actually covered, we got partway through demand paging before we took the second exam. So there's a little bit of that demand paging material that we didn't get to cover, or we didn't get to cover on the second exam. I'd go back and have a look at that because that might be something easy to overlook. I'm laughing because, like I said, usually when the questions dry up, I just start talking about random stuff, which feels silly to do on video. But I had access to my whole basement worth of stuff, which I could show you some things from my basement live. Buffer weapons. I've got 2 kids that are not young kids anymore, but when they were younger kids, we learned how to make fake foam weapons. So we got a whole tub full of fake foam weapons that don't get used as much as they used to. So these are just 2 examples. I could show you another. That was not expected. Well, you are in for a surprise because I also realized that here in the basement, I have my gallon jar of Tabasco sauce, which lasts a long time. I mean, you don't dispense directly from the jar. You keep the jar and then you fill smaller jars from it. And when you get a gallon jar of Tabasco sauce, you can get your name put on it. All right, that cost us some people right there. All right, so just to confirm, CLOOK goes all the way to index 0 for the cylinder. No. So the question about CLOOK versus look is, I really think you're asking about scan versus look. So we've really got 4 disk scheduling algorithms that are all pretty similar. They vary on 2 qualities. The scan guys always go to the outermost cylinder, and then they go back to the innermost cylinder. So even if they've passed the last request, they keep going all the way to, I think of it as the edge of the disk. Whereas look doesn't do that. Look is, you could think of it as being lazier. When it gets to the last request, that's when it turns around. Even if there are other cylinders out there, if nobody wants anything on them, it turns around. So scan versus look is whether or not you go all the way to the edge of the disk or do you stop at the last request. The C part is whether they're circular or not. For C-scan, it services request in a direction, and then it runs all the way back to the start of disk and then takes another pass servicing request. And as long as requests keep coming in, it'll keep having new requests to satisfy as it does that. Same with CLOOK. CLOOK only serves requests in one direction. It's just when it gets to the last request, it turns around and runs all the way back to the first request, not to the first cylinder on the disk. Runs back to the first request and then serves them in one direction. Yeah, so I see an answer to a question that I didn't see the question for, but I think someone is asking what the weight is on the different parts of the semester. And I usually try to shoot for 30, 30, 40%. I don't know if I always do a great job of that, but I do try to put more weight on the stuff at the end because we haven't previously been tested about that. Yeah, so there's another answer to the same thing. What direction do you fill? What direction do you fill the stack from in TLB paging? I don't understand that question. I'm looking at the question that says, what direction do you fill the stack from in TLB paging? TLB is probably short for the translation look-aside buffer, and it's important. And I guess maybe we had one question in class, or we had a slide in class, where we had a tiny little 2-element TLB, and we pretended that it was getting populated as we were doing address translation. And there we just filled them top to bottom. You might also be asking about page replacement algorithms, where if we drew a bunch of little boxes and we pretended those were available frames of memory, we always fill them top to bottom. And if I give you a question like that on the exam, I'll probably say to do it that way, or I'll expect you to do it that way, because otherwise it's hard to grade. I don't know how to grade that question, but if we can get you to do it in the same order that we do it, then your answer should match ours. Will the Tabasco sauce fact be on the exam? If it is, it'll only be extra credit, and it'll be worth an infinitesimal amount of extra credit. This is the greatest part. I assume that's the tour of the basement. I think that's all I got to show you from the basement, though. Like, if there was another slow moment, I would, I don't know what would be next, unless I just saw an item. Can we invoke the right of grade by combat? That's a reference to something, I think, but I don't know what it is. I would not want a grade by comment. That is, I would not want to be on my end of grade by comment. Tabasco sauce, extra credit question. Yeah, we addressed that. Spicy. That is not the usual Tabasco. That's the Chipotle Tabasco, which is a lot milder than the regular stuff. For purposes of victim selection. Okay, so that's back to the previous question about the TLB paging. So which direction you go to fill the stack from in TLB paging for the purpose of victim selection? I still don't know if I understand the question. This may be, so when we talk about victim selection, we're usually talking about, actually, I think that phrase showed up twice. Once is when we're doing deadlock detection and recovery. I think picking the process to kill is called victim selection. But I think you're definitely talking about it with page replacement, where you got to pick someone, once memory's full, you got to pick someone to kick out to make room for a new page. And I guess, I don't know if this is what you're asking, but when we had two algorithms that kind of looked in a particular direction, if we had a reference string, make up 3, 2, 5, 1, 7, 9, 2, 1, and let's say we page fault and we bring in this guy, or we need to bring in page number 1. The optimal algorithm says to look ahead to pick the page that won't be needed for the longest amount of time in the future. But just like the optimal scheduling algorithm, that requires knowledge of the future, and the OS can't generally have that. So our next option was LRU, least recently used, which is kind of the same idea, but instead of looking ahead, we're going to look back. We're going to pick the page that hasn't been used for the longest time. We can at least do that. At least that's at least possible. And this may be what you're talking about. You can think of one of them as forward-looking and one of them as backward-looking. I thought about that also. So I'm reading a comment that says victim selection is a reference to grading by comment. And for a moment, I thought that's what it was about, but I looked back and found another post by the same person. I brought myself a chair. Want to see another item from the basement? It's my Star Trek Next Generation lunchbox. There you go. You can see the big three: Wesley Crusher, Jean-Luc Picard, and Lieutenant Commander Data on the set. I'm looking at the question about the protection and security stuff. Probably a lot of it will be vocabulary. I think about things like the trade-offs. Remember, we spent that little bit of time talking about Unix mechanisms for storing permissions and how they work. And I don't know if that's really vocabulary, but I think I could probably ask you a question about that. We did the confinement problem. I don't know if I've ever done it, but it seems like you could show someone an access matrix and then ask them about whether or not it would be possible to obtain a particular access right, kind of like the one example we did in class. And I could probably make one of those that required a little bit of thought, but I don't feel like I could really make it too hard because that's not, I'd say that's not super central to what we did. But I mean, there's another term that you'd be expected to know that idea of the confinement problem. So there's a request, that last request for doing address translation between logical and physical spaces. I don't know if I can fit an interesting example on my whiteboard, but let's give it a try. Let's see what we can do. I'll be right back. All right, so if we are so it seems like if we're just going to make up a question, the place to start is to make up a page table. Usually, to fit on exam, we have to make a tiny little page table. So that's. But what bits would we normally want to have? We probably normally want to have a valid invalid bit and a read-only bit, just to make the question interesting. And then probably this last guy, we're going to say, well, that's a prime number. And then let's just let's make a bunch of rows for this. All right. And then if I was making up this question, at this point, I would just make up some stuff. I probably want some frames that are, or some pages that are valid and some that are invalid. And if the page is invalid, the rest of this doesn't really matter because you're not going to be able to use it for address translation. So, I might fill those in with zeros, or I might fill them in with non-zero values just to see if that throws anybody. But if it's invalid, then the rest of that doesn't matter. You could think of it as just being uninitialized memory. All right, and then for the valid ones, I probably want some that are read-only and some that are not. I was going to use those in the question. I'm changing my line on that one. And then I would just make up frame numbers. You can see I pretended the frame number is 5 bits here, so I'm going to stick with that and say, well, this guy is I don't think I did any duplicates there. You could have duplicates. I mean, you wouldn't normally expect it. But if you had duplicate frame numbers, that would just mean the same thing showed up in more than one place in your logical address space, which, well, maybe there's some cases where that could be useful. All right, and then I'll just start making up logical addresses. But I can't make ones that are very big because my page table only has 6 entries. So let's pretend we're making a logical address where the high order 3 bits are page numbers. So we could go with something like, let's do one, so I'm just thinking, let's do one that goes to here. So that's line 5 of the page table if we count from 0. Then binary of 5 is 0, 1, 0. And then if this is the page number, any of the remaining bits would have to be offset. And I'm pretending I've got, I'm just making up the question so I can fill in the explanation later. But I'm pretending we got bits of page number and 6 bits of offset. If I was asking this question, You know, it wouldn't get described in that order. It'd be kind of described saying, oh, pretend you got a logical address that's 9 bits long, and the page size is 2 to the 6th bits. And the reason I said that is, well, you got 6 bits, and you got 6 bits of offset. So for this address to work like I planned for it to work, those bottom 6 bits have to be addresses within a particular page. So 6 bits are offset within a page, then a page is 2 to the 6th addresses in size. I hope I said that right a moment ago. I hope I didn't say a page is 2 to the 6th bits, because that'd be a bad way to say it. So here we're pretending that every page is 2 to the 6th addresses, or 2 to the 6th bytes in size. All right, so let's pretend this is a write. I'm running out of space here, so I'll just put a W to this particular address, logical address, and that's your page table. What does it translate to? Well, because of what the question said, because we're assuming a page is 2 to the 6th bytes in size, that says those are your offset. So that stuff, the 101 is your page number. That's binary for 5. And then we're just kind of undoing what I did when I made up this question. So that's 5, so that's entry 0, 1, 2, 3, 4, 5. So that's the line of the page table that says what this translates to. It's valid, so you can access it. It's not read-only, so this is permitted. And that's the frame where it lives in memory. So you take we're going to build a logical address where that's the frame we're going to, and that's the location within the frame, the offset within the frame. So to build the final logical address, I just copy down the frame number, 11001, and then the offset, 0001111, and that's what it translates to. Let's do another example real fast, because we should pick one that's invalid. So I think I'll go with, what if you had a read to address 0, 1, 1, 1, 1, 0, 0, 1, 1. So I just made that up, but while I was making it up, I was thinking about that line of the page because it's invalid. And I wrote down an address that mapped to page number 3. That's these 3 bits. So 1, 0, 1, 2, 3. So that guy's invalid. And like I said, when I was making this table, the rest of that stuff doesn't matter because you can't use it for address translation. So this would be an invalid address. I'm catching up on the comments. So I'm looking at the one that says, can we do a TLB example? I don't want to do that, but we will if we need to. I'm looking to see if there are any other questions. Can you explain the working set model and locality of reference? All right, let's do those last two because that's just talking and that might go faster. So the working set model is a way, I guess we got to that idea from talking about thrashing. And this idea that if a process doesn't have the pages that it needs in memory, it's not going to run efficiently because it's going to keep page faulting. The working set model says at any given time, a process has a set of pages that it's actively using, and we're going to call that its working set. We could compute the working set of a process just by looking at all of the pages it's referenced recently, where recently might mean in the last, say, 10 million memory references. And we could just try to make sure that either it has all of those in memory, or if it doesn't have them, we might as well not run the process for now. We might as well just set it aside until memory is less scarce. So that's where we got the idea, and you could look at, I think your book has a neat picture that shows the memory reference pattern of a process And it sort of shows, well, at different times, there are different regions of memory that it's really using. But when it starts doing something different, like entering a different phase of computation, its working set changes. So you could implement that in principle, but if you tried to measure in practice, if you tried to measure the working set of a process exactly, really know what pages it's used in the last, say, 10 million memory reference, it'd be too expensive. Just like implementing LRU perfectly would be too expensive. So then we settled for this idea that we could do about as well by just monitoring page fault rate. And you may remember there was a little graph that we looked at on the slides. I think it's a graph out of the book that shows that as we give, and I'm not going to label this, I don't have enough room, but this axis was number of frames, and this axis was page fault rate. And this graph kind of says, oh, you would expect that as we give you more frames, you're not going to page fault as much. But the interesting part of this was saying, oh, we could make two thresholds. One, where if your page fault rate drops below this threshold, then we're going to take back some frames, because maybe you have way more than you need. And another threshold that said, well, if your page fault rate gets too high, we're going to start giving you more frames, because obviously, even if we don't know exactly what your working set is, obviously you don't have enough pages to keep your whole working set in memory, so you're not going to run efficiently. I'm looking back at the question to see, all right, so can you explain the working set model? And that's what I just tried to do. Locality of reference. I probably didn't do a great job describing that in class, because it's the kind of thing that I assume you've seen in previous classes. It's this idea that if you I'm trying to pick the right way to say this. Often you hear people say, if you exhibit good locality of reference, or if your program is written taking locality of reference into consideration, it's going to run more efficiently. And that just says that instead of randomly accessing all the memory within your processor, instead of, I guess, uniformly using every byte of your logical address space, at each point of computation, you're going to have a small set of your memory that you're actively using, so that if you access a byte of memory, there's a good chance you're going to want to access that byte again in the future. So if I can get that in memory and keep it there, you'll run faster next time you access it. And if you access a byte of memory, there's also a good chance you're going to access nearby bytes of memory. Those are the same ideas we talked about probably the first week of class when we were talking about caching. And we said, well, that first one was temporal locality. If you access a byte of memory, you're probably going to want that byte again in the future. And if you do, cache can speed, if that's true, cache can speed you up. And the spatial locality is that other one. If you access a byte of memory, you're probably going to want nearby bytes in the future. And if you're going through like a linear data structure like an array, you're probably going to exhibit good spatial locality. I don't know if that answered the question, but locality of reference just means you're likely to heavily use a small subset of your memory at any one time, again, rather than trying to use it all at once. All right, now I'm going back to the question that I said I didn't want to answer, and that is, can we see an example of trying to use a TLB? Let's try and tack that onto this one. I don't know if it's going to be super interesting. Here, the problem with using, I'm just trying to think, to see the TLB do anything, we've got to kind of get something into the TLB, and then we've got to try to use that again. So we'll continue using the same page table. I'll make up a few more memory accesses. All right, so I've got to write to that page. Let's make a read to let's do so pretend these are happening in order. We're going to write, we're going to read, sorry, we're going to read, we're going to write. Let's put in another write to this. And just thinking about what I'm trying to do for the TLB to see it doing anything interesting, we got to kind of have at least more than one reference to the same page. So that's why I snuck in and you can see I made this guy access the same page as this. All right, so how does the TLB work? Well, let's say you did this reference to memory, so you're doing a read from page 1. That's this guy right here, but before you go to the page table, because that's stored in main memory, and accessing it is just as slow as accessing main memory. So the idea is CPU designers will build a TLB. I did some, I mean, this is just an aside, I did some reading about this, and modern CPUs looks like they have multiple TLBs, just like a lot of other caches. Smaller, faster ones that are closer to the CPU, and bigger, slower ones that are, I guess, closer to main memory. But we're just pretending there's one TLB, and so when you access this page, we're first going to consult the TLB. And let's pretend, this is unrealistic, but let's pretend it's got 2 entries. So you go to the TLB, maybe it doesn't have anything in it, and you say, oh, I've got to know where page 1 lives, so now we have to go to the page table. And that's expensive, so that's the whole reason we have the TLB. But if we're going to do that, why not populate the TLB? So in the TLB, we're going to remember, oh, if you ever need page 1 again, it lives in frame 00111. Oh, and it's valid, and it's, well, actually, I apologize. I'm doing page 1, but I accidentally copied this line down. This is the only place where it matters. So I copied that from the top line of the page table, and I should have been on this line. So it lives in frame 01, 10101. It's valid, and it's read-only. You need that in the future. As we said in class, it wouldn't be super important to have this valid flag here, because if it wasn't valid, you never would have been able to access it anyway. But it doesn't really hurt to have it there. All right, and then maybe we'll skip the translation part, or maybe we'll just do this one and we'll skip it on the other ones. And then once the TLB is populated, now you can translate this address. You can say, oh, my TLB tells me page 1 is valid. It's read-only, but I'm only trying to read it, so I'm okay. And it lives in this frame, so that translates to page number, sorry, frame number 10101, and then offset 0111110. It's shaky, but that's what it translates to. Moving on to the next one, when you access, if this is your next instruction, it's an attempt to write to page number 5. We consult the TLB, it's not there. So we're going to populate the TLB from the page table. That's expensive, but we'll cache it in the TLB for the future, so we won't have to pay that expense twice. So we think that TLB is remembering, oh, if you ever need page 5 in the future, it's valid, it's not read-only, I'm just copying from here, and it lives in frame 11001, and then that'll let us translate this address. We won't bother doing that, but it would just be those bits glued together with those bits. And then we have a write to page 1. We look it up in the TLB, and whoo, it's a TLB hit. So I think an important thing to appreciate here, it's true of any cache, is a cache holds a subset of whatever's in backing store. Well, in this case, it's holding a subset of what's in your page table, but it can't hold the whole thing. So typically an entry has to somehow say, oh, this is an entry for line 1 of the page table. This is an entry for line 5. So we didn't need that in the page table because it has every line. So if you want to know what's in line 1, it's right there on line 1. If you want to know what's in line 5, it's right here. But since the TLB is holding a subset of what's in the page table, For every entry, it has to keep up with, oh, this is an entry for this page or for this page. All right, so this last example is an attempt to write to page 1. Oh, good, it's in the TLB. Page 1 lives in frame 10101. It's valid, but it's read-only. So this would fail to write the page because that's a page you're not permitted to write. But it would do it without having to go to the page table because I tried to construct this example so that when you access this entry, you've already stuck it in the TLB. So I'm going to say that's an okay answer to the question about populating the TLB. This is as far as size. This is a lot like what we did in class. I think in class, we probably had one more example where we had to talk about, well, once you start accessing other stuff, the hardware is going to have to start throwing things out of the TLB. And we could add another example for that, but it would force us to pick out one of these if we had to bring in something else. All right, other questions? This has gone on longer than I expected, but I'm guessing we've lost a few people. Oh, we just lost a bunch of people. I'll look around my basement to see if I have anything else unusual. Here, we could play a game. Does anyone know what this is? Right here. Roughly spherical. Marble toy? I am getting answers. I didn't expect that. But so I'm a little surprised that so many people know that it's an ice cream maker. You fill it up with ice cream ingredients, and then you kick it around in your backyard, which is a bad idea, we've learned, because it's made of hard plastic. And if you kick it too hard, you're going to hurt yourself. Don't you spin it around and run a marble down. I agree that it looks like that. The toy where you're supposed to navigate a maze, and it looks kind of like that. And maybe the resolution wasn't that good, but it's an ice cream maker. All right, are we done? I don't know how to answer that question. Is that a gerbil ball? It's not a gerbil ball. You'd have to be a muscular gerbil to drive that thing. I thought about that. So I'm looking at the juggling question. Maybe I'll bring something to class. The risk is that if I started juggling and stuff started flying around, that my nice whiteboard over there and the impromptu stand that my laptop is on might come crashing down. So I'm going to err on the side of caution there. I'm looking at the comment about the banjo playing. I did buy some fresh strings for the banjo, but that doesn't make me a good banjo player. All right, so it's been about 2 hours. I'm going to say, let's call it an evening. Thanks for your questions. Thanks for your patience as I started showing you random items from my basement. And good luck at the exam. I know you're probably taking a bunch of them. And good luck with all of them. I'll see you in class in a day or so.